Good afternoon, I'm Frederick Brown, and today I'm going to explain how to solve a combined spectral problem. The given formula for this problem is C7H14O2. For this formula, we are given the IR spectrum, the CNMR spectrum, and the HNMR spectrum. Our first step to completing this problem is to determine the ratio of our carbons bound to our hydrogens. This will help us to determine if there are going to be any rings or pi bonds. These outcomes will be indicated by any hydrogens missing from the formula. We would also consider any halogens or nitrogens present in the formula, but since our formula does not have any, we do not need to worry about them. The formula for this is 2n plus 2 with n representing the number of carbons. So we have 7 carbons, so that would be 2 times 7, which equals 14, plus 2, which equals 16. Then we will subtract our 14 hydrogens, which would give us 2, and then we divide that by 2, which would be 1. So the value of 1 tells us there is a pi bond somewhere in this molecule. Now we can take a look at the infrared spectrum or the IR spectrum to figure out what kind of functional groups will be present in our molecule. First, let's look at the region of 2500 to 2000, so this area here. This region is where any triple bonds will be present. Since we do not have any peaks, we can say that there's no triple bonds present in this molecule. Next, we'll take a look between the double bond region, which is located between roughly 2000 to 1500. We have one long peak, which is right here at roughly 1730. This most likely indicates a carbon double bonded to an oxygen. Then if we look at around 3000, we see another peak that is between 2800 and 3000. This peak here indicates that there is an sp3 carbon bound to a hydrogen. In this information, it seems that we are starting to see that we have some kind of alkane with a carbonyl group of some type. And then next we can see, look at the 3500 area, where we can rule out the presence of any OH groups, since there's not the signature big broad peak associated with the OH groups. And then lastly, if we look now at the peak around 1200, this is the area where we will see any carbon single bound to an oxygen. So this is where we can get and find our second oxygen of the molecule right here. Everything to the right of the 1000 is considered the footprint of the molecule, and we don't need to worry about any of this because it doesn't give us any helpful information. So next we will look at the CMR, which is here. So looking at the CMR spectrum, we see that we have 6 signals. So 1, 2, 3, 4, 5, 6. So those are the 6 carbons. Given that our formula has 7 carbons, we know that 2 of our carbons must be identical so that they are only giving off 1 signal. So when looking at the CNR spectrum, the closer the x-axis is to 0 parts per million is considered upfield, and the closer the x-axis is to 200 parts per million is considered downfield. This helps us figure out how close a molecule is to an electronegative atom. So the farther downfield, the closer the molecule is to an electronegative atom. So with this, we can interpret the signal at roughly 172 parts per million as the carbon double bonded to an oxygen, or the carbonyl carbon that we found on the IR spectrum. It is the closest to both oxygens. And then the higher the peaks involved here on this spectrum shows the signal, the signal that's more shielded. That carbon is from the electronegativity of the electronegative atom. So we can see this by the peak of the roughly 22 parts per million signal being the most shielded. Next we can look at the HNMR spectra. We can see the number of signals that we have for this molecule. Based off of the HMR, we have 5 signals, so 1, 2, 3, 4, and 5. So this means that we have 5 different types of protons in our molecules, or in other words, we have 5 unique carbons bound to hydrogen. These signals show us symmetry within the molecule. Knowing how many unique carbons we have helps us because looking back at our formula, we have 7 carbons. So knowing that we have 5 unique tells us that there's going to be some kind of identical group, like 2 methyl groups bound to 1 carbon, or the presence of the carbonyl that we have already found in our spectrum. So how we read the IH NMR is by looking at the x-axis, which is in parts per million, just like the CNMR, and it shows us the chemical shift, which tells us how shielded the nucleus of a molecule is and the overall difference of the frequency between different groups. Then we can look at the spin or multiplicity, which is the number of peaks in each signal. So looking at the first one here, signal here from left to right, we have 4 distinct peaks, so 1, 2, 3, 4. Within the signal at 4 parts per million, these peaks refer to how many neighbors the hydrogen has, or tells us how many hydrogens are attached to the next carbon on either side of the carbon represented by the particular signal. The formula we use is n+1, where n stands for the neighbors, to figure out how many peaks will be shown. So looking at my proposed structure here, we'll have different signals. So this will be signal, these hydrogens here will be one signal, this one will be signal 2, signal 3, these will be signal 4, and then signal 5. The 2 methyl group hydrogens attached to the first carbon are identical, so these here are identical, so they are in the same group, which we'll label as which I labeled as 1. The next lone hydrogen attached here would be group 2. These would be group 3, group 4, and then group 5. So looking at the hydrogen of group 1, they have 1 neighbor. So these here have, on this carbon, has 1. So that'd be the formula using n+1, we get 1 + 1, which equals 2. So this is a doublet when looking at the graph. We can distinguish it, so it'll have 2, so 1, 2, and we have 2 doublets on this spectrum, but the carbons we're looking at, there were 6 of them, so it's going to be this higher peak. So this would be, when labeling, we would label this as 6H, standing for 6 hydrogens. And then we can continue to go through the rest labeling based off of their locations on the molecule. So as you can see, with our graphs, my IR frequencies I labeled found between 2800 and 3000 was our CH sp3. Roughly around 1730 was our carbon double bonded oxygen, and then at 1200 was our carbon single bonded oxygen functional group. On our CNMR, roughly at my chemical shifts were at approximately 12, 22, 26, 42, 60, and 172. And then these are the bonds that they are associated with. Here is our HMR. So our chemical shifts were approximately at 0.9, 1.2, 2.2, 2.4, and 4 parts per million. The interrogation is like what I labeled with the 6 hydrogens. So it's telling you how many hydrogens are in that group. So we have 5 groups. And then the doublet is telling us how many neighboring hydrogens they have. And then these are the interpretation of the groups that they are associated with. And then, based off all this information, this is the proposed structure that I came up with. So you have that carbonyl group and our single bonded carbon that we found. And then, so this is an ester of some type. I hope you found this to be informational and helpful with regards to solving a spectral problem. So,